Welcome to the 17th chapter on game proofs and separations in the Logical Foundations of Cyber-Physical Systems textbook, where we're continuing our investigation of hybrid games and differential game logic by comparing proof principles for hybrid games versus those of hybrid systems. In particular, we'll be contrasting and identifying what the exact difference is between reasoning about hybrid systems compared to hybrid games, which, despite being rooted in very different semantics, it turned out in the previous chapter that hybrid games' axioms are shockingly close to those of hybrid systems, and we should take a note of the fact, as we're developing it in this chapter, that there's nevertheless some rather major soundness critical discrepancies, which are, of course, very important to get right in order to make sure that we correctly reason about hybrid games, but they also shed a complementary light on reasoning principles for hybrid systems because they'll highlight which of those reasoning principles crucially dependent on the absence of adversarial dynamics. Remember, in the 14th chapter, we've introduced the syntax of hybrid games and differential game logic. In the 15th chapter, we took a deep dive on developing the winning region semantics for hybrid games. In the 16th chapter, we achieved a major breakthrough in the understanding of hybrid games by studying their axioms. So even if the semantics turned out to be surprisingly subtle, the axioms looked pretty tame. It was surprisingly easy to prove correctness properties of hybrid games with differential game logic in ways that were actually quite similar to the ways that we've proved properties of hybrid systems before, just in differential dynamic logic instead of now differential game logic. Well, of course, come to think of it, it should make us wonder a little bit why two logics that are based on such very different semantical conditions, hybrid systems versus hybrid games, end up being so surprisingly close as far as their axioms are concerned. In particular, that's how we will look at now at also the differences of the axioms. So how does the difference in semantics reflect in a difference in reasoning principles? And we will find quite surprising logical robustness that even though both of those classes of systems and corresponding logics are based on semantically quite different bases, they still end up having pretty similar axioms at the end of the day regardless. What we're learning on the modeling and control side is admittedly not that much in this lecture. But regardless, in the second part of this lecture, we'll do an interesting, exciting detour with an expedition into mixing continuous and adversarial dynamics in the form of differential games, where game aspects happen during a differential equation as opposed to during the hybrid systems dynamics only. We'll also look at better understandings of how systems and games differ. But on the computational thinking side, we'll devote a lot of attention again to the rigorous reasoning for adversarial dynamics. Not because we will be developing new reasoning principles for hybrid games, because we've seen all of those in the previous chapter already, but because we will be aligning them, which of the ones are different in hybrid systems compared to hybrid games. Well, we will experience the miracle of soundness and separate sound reasoning principles for hybrid systems from sound reasoning principles for hybrid games. We'll also understand that we actually have an axiomatization of differential game logic by taking multidynamical systems principles at heart. We will study an extension of differential invariance to these differential games I mentioned a moment ago, differential game invariance. And we'll also appreciate a surprising robustness of logic, that even if we start out with fundamentally very different types of systems, the reasoning principles get close together regardless. And that's a bit of a miracle too. But it gives you a lot of hope that if you are interested in yet another new type of multidynamical systems, prepare to do a deep dive on its semantical developments, but also come up with the hope that at the end of this development, as we have now seen for hybrid games, you emerge with a logic that fairly robustly enables you to continue reasoning principles that are still sound for your augmented enriched class of multidynamical systems. On the CPS skills side, we'll develop a complementary understanding of the semantics of CPS models, in particular how they're impacted by the presence or absence of adversariality. In particular, since we see a syntactic characterization of the difference in reasoning principles for hybrid systems versus hybrid games, that will enable us to more easily pinpoint where exact nuances in different CPS operations and arguments are placed. We'll also, by looking at differential games and differential hybrid games, look at the phenomenon of multi-scale feedback in systems. So how feedback from other agents or players in the system can happen at different paces, some very quickly, and others extremely slowly in comparison. Remember, we've seen differential game logic with the hybrid game language and the differential game logic formula language, where most operators are, as usual, discrete assignment, testing a logical formula for whether it's true at the moment, which is Angel's fault if Q isn't true, following a differential equation under Angel's control within the region where Q is true, a game of choice between alpha and beta that Angel gets to decide which side she would like to play, a sequential game where you first follow the game alpha and then you play the game beta, the repetition game where Angel is in charge of repeating alpha any number of times she sees fit, and most importantly, the dual game, where now the entire control is flipped around, such that every decision that Angel had, now Demon does have, and every decision Demon did have, now Angel does have. The roles of the players flip like in pretend play. The differential game logic formulas, sort as they always do for us with real arithmetic and propositional logic and quantifiers of the reals, but most importantly, the alpha diamond P formula means that Angel has a winning strategy in the hybrid game alpha to get to one of the states in which the logical formula P is true, while alpha box P means that Demon has a winning strategy in the hybrid game alpha to get to one of the states where P is true. The syntax, however, really was a very tame extension of that of hybrid systems, with the presence of the duality operator being the only thing that ever changed. That, however, led us to develop the semantics of differential game logic in hybrid games, which was markedly different, in particular because during the hybrid game semantic development, we had to make sure we develop a winning region semantics, which is perfectly denotational and easy after the fact, but still, it was important that we simultaneously develop it for the set of all the states into which we would like to win, for example, by saying that the meaning, the set of all states where alpha diamond P is true, is the winning region corresponding to the hybrid game alpha, for the winning condition being the set of all states in which the post condition happens to be true, which we then pass in here by induction. The only really still subtle case was the repetition case, where we ended up with the least fixed point condition. But, okay, the semantics were kind of hard in comparison to the syntactic change, because we had to be prepared for the fact that even the, for example, choice operator needs to be prepared for the fact that its sub-games are still games, so there's adversariality happening, even if the game choice itself is at the moment just for one player. Now, in the axiomatic development, we sort of recovered from that phenomenon, because when we developed the axioms of reasoning about hybrid games, they look pretty tame. In fact, they look just precisely how the axioms for hybrid systems look to us. For example, Angel has a winning strategy in a game of choice between alpha and beta to get to a state where P holds true, if and only if Angel has a winning strategy in the hybrid game alpha to get to a state where P holds true, or Angel has a winning strategy in the game beta to get to a state where P holds true. And the others as well. We all justified them and they were quite fine. Now let's understand with more care how hybrid games proving works, and in particular how it compares and contrasts with hybrid systems reasoning. First of all, we've seen these axioms for differential game logic, but we shouldn't be adopting any axioms without having done a proper soundness argument for it. In fact, if you look at the textbook, it already did that in the previous chapter. But let's make up for that right now. So how do we convince ourselves that the differential game logic proof calculus is actually sound? What does soundness mean? I remember. It means that every axiom is sound, which means every axiom has only valid formulas as instances. But what it really needs to be able to demonstrate is, of course, that a proof calculus is sound whenever every formula it ever proves is a valid formula. So the formula is true in every state. Well, do we have to prove anything at all for that? All the axioms we saw were perfectly familiar. Couldn't we have arrived at those axioms in much easier ways? Come to think of it, that they're all the same as they have been before in hybrid systems land? Well, let's understand this in more detail. In fact, before we go any further, let's write down axioms that we've seen in hybrid systems land already and convince ourselves that they're still fine in hybrid games land, and then go for a soundness argument for all of them at once. Now, the first one is Kripke's axiom, the modal modus ponens. Okay, where let's first read them as a hybrid system, and then let's read them as a hybrid game. All ways of running a hybrid program alpha are such that P implies Q afterwards. Then, if all ways of running the hybrid program are such that P holds true afterwards, then of course all ways of running the hybrid program alpha are such that Q also holds afterward, because P implies Q together with P implies that Q is true. Now, let's read it as a hybrid game. Demon has a winning strategy in the hybrid game alpha to make P implies Q true. Then, if Demon also has a winning strategy in the hybrid game alpha to make P true, then he does have a winning strategy in the hybrid game alpha to make Q true. The monotonicity axiom has two implications, this direction and that direction. One of them is called the converse monotonicity axiom, and that one is the forward one, which says that red is a hybrid system. If there is a way of running the hybrid system alpha to a state where P or Q is true, then there is a way of running the hybrid system alpha to a state where P holds true, or there is a way of running the hybrid system to the state where Q is true. And this is precisely the backwards implication direction. Now, let's read them as a hybrid game. If Angel has a winning strategy in the hybrid game alpha to make P or Q true, then she either has a winning strategy in the hybrid game alpha to make P true, or she has a winning strategy in the hybrid game alpha to make Q true. And likewise in the backward direction. Now, induction axiom, first read as a hybrid system, then as a hybrid game. All ways of running a repetition alpha star to get to a state where P holds true is true if and only if, well, first of all, P has to be true right now. Otherwise, after not repeating alpha any number of times, is it already false? And no matter how often we have repeated alpha already, if we're still safe, then we're safe after running one more round of alpha. Here's the induction proof rule. Now, the Barkan axiom and the converse Barkan axiom, named after Julia Barkan, not for differential dynamic logic or differential game logic and simpler modal logics, but still it's the same kind of idea. If there is a way of running hybrid program alpha such that there is a choice for the variable x to make P true, then there is a choice for the variable x to get to a state where there is a way of running the hybrid program alpha to a state where P holds true. So the Barkin axiom flips like-minded modalities and quantifiers around in this direction or in that direction. And now red is a hybrid game. If Angel has a winning strategy in the hybrid game alpha to get to a state where there is an x such that P is true, then there is an x such that Angel has a winning strategy in the hybrid game alpha to get to a state where P holds true, and likewise backwards. Gödel's proof rule: if P is valid, then after all ways of running the hybrid system alpha is P true. Well, because P was true in every state, so also in all the states that we reach after having run the hybrid program alpha. Now, when red is a game, wait, let's see what that means. So if P is valid, then Demon has a winning strategy in the hybrid game alpha to get to a state where P holds true. Really? Well, but what if actually, but clearly in every final state is the postcondition true, because the postcondition is true in all the states of the system. It's something like true or x squared greater than 0, so that's very easy to satisfy, really seriously. But does Demon have a winning strategy to make it to a final state? Ooh, well, what if Demon was supposed to succeed in passing some tests or evolution domain constraints with an alpha? What if, for the sake of the argument, Angel was able to trick Demon in the hybrid game alpha to violate the rules of the game prematurely? Then he would have lost prematurely, and then there is no final state in which we would check whether P is true, even if P would be true in every final state. So actually, that doesn't seem so good. Gödel's generalization proof rule is not actually sound for hybrid games. And come to think of it, maybe previous axioms, maybe there were also some subtleties that we glossed over. Let's worry about the Barkin axiom again. If Angel has a winning strategy in the hybrid game alpha to get to a state where there is an x such that P, does she then ahead of time have a way of picking the x and then have a winning strategy to make it to precisely that P? Well, it is commuting modalities and like-minded quantifiers are right, of course, if the variable doesn't occur either read or written in the hybrid game alpha, just like it shouldn't occur in the hybrid program alpha. But wait a second. Just because after applying the hybrid game alpha, Angel has a way of picking an x that won. So for example, if the formula says, is there a way in a robo-soccer tournament to name the robot that has scored the maximum number of goals X? Well, that should be easy enough for Angel to do, but does that mean she could name the robot who has scored the maximum number of goals X ahead of time and then have a winning strategy in the hybrid game alpha with the robot soccer tournament to make sure that the particular X she chose really has the maximum number of goals? That sounds pretty hard. Here she can just wait it out and name the X, but that doesn't mean she would be able to predict it ahead of time. This is like, betting on horses. After you've been betting on horses, it's very easy to say, yeah, I know who won the horse race. It was Lucky Star. But ahead of time, this is really hard. In fact, that's usually called cheating. So I guess that axiom, the Barkin axiom, isn't actually okay for hybrid games. Well, what about the converse Barkin axiom? If there is an X such that Angel has a winning strategy in the hybrid game alpha to make it to a state where P holds true, In other words, ahead of time, she already knows the X that will do it. Then she can wait until after the game to reveal the fact that she already knew the right choice for X. Well, that's easy, right? If you happen to know things ahead of time, you can just not tell anybody yet and wait. So that direction is a good one. Okay, that one is good. In fact, well, Gödel's proof rule we decided was a bad one. What about the monotonicity proof rule? That looks pretty similar, just has an extra assumption here. Because if P implies Q, then Demon has a winning strategy in the hybrid game alpha to get to P, and if that's the case, then he does have a winning strategy in the hybrid game alpha to get to Q. Well, that makes sense, because if Demon has a winning strategy in the hybrid game alpha to get to P, then apparently Angel can't always fool him into losing the game by tricking him into violating the rules of the game. So the monotonicity thing is all right. Okay, but I guess we should really look back more carefully. How about we start at the beginning here with the Kripke axiom again, and make sure no matter how sound it was for hybrid systems, it's still okay for hybrid games. So if Demon has a winning strategy in the hybrid game alpha to make P implies Q true, then if he also has a winning strategy in the hybrid game alpha to make P true, does he have a winning strategy in the hybrid game alpha to make Q true? Well, let's see. For example, in robot soccer, right? Demon has a winning strategy to make sure that every time his robot kicks a ball, he scores a goal, just never even kick. That's easy enough. Does he have a winning strategy to also always kick the ball? Sure, just kick it in random directions, but does that mean he has a winning strategy to score a goal all the time? No, because the winning strategy he had to choose to make sure that whenever he kicks the ball, he scores a goal, namely never kick, was a very different one than the winning strategy he needed in the exact same RoboSoccer tournament to make sure he always kicks the ball, which was, well, kick in arbitrary random directions. And they don't fit together into a winning strategy to always score goals, even though that would be amazing. Please work on it. So that axiom also doesn't really work for hybrid games. It would be unsound. Now what about the monotonicity proof rule? Well, that's very similar, and we already saw it is fine down here. So it's still going to be fine up here as a counterpart. But notice here in particular, we prove once and for all that P implies Q, not just P implies Q after a certain winning strategy, and then it's fine that this indeed implies that, as is written over here. Monotonicity axiom. Let's read that again very carefully. If Angel has a winning strategy to make P or Q true, then does she have a winning strategy to make P true or a winning strategy to make Q true? No. Think of a robot scenario, the Wally and Eve scenario. If Angel playing Eve has a winning strategy to keep Eve's robot either close or far from Wally, well, because every particular scenario is either close or far, does she have a winning strategy to keep her robot always either close, or have a winning strategy to keep her robot always far apart? No, that's much harder, because she'll have to choose one of the two and say, let me always get close, or let me always be far, and that's very difficult in comparison. So that also actually isn't a safe, sound axiom for hybrid games. What about the converse direction of monotonicity? Well, if Angel has a winning strategy in the hybrid game alpha to get to P, or if she has a winning strategy in the hybrid game alpha to get to Q, then either way, she has a winning strategy to get to P or Q, because she even has a winning strategy to consistently go to P or to consistently go to Q. So certainly the disjunction will be a piece of cake. So that one works. Maybe we should worry about the induction axiom more carefully yet again. Is it okay for hybrid games? Demon has a winning strategy in Angel's repetition of alpha to make P true. Well, that certainly means it's quite necessary for P to be true right now. Otherwise, Angel would just stop the game right away and Demon would have lost. So P has to be true, that's clear. And then, is that really equivalent to also knowing that Demon has a winning strategy in the repetition to make it to a state where if the invariant P is still true, then Demon has a winning strategy in the hybrid game alpha to make it to P? Well, not really. For example, let's say this is a robot soccer race, and you're trying to make sure not to run out of energy. Certainly you haven't run out of energy right in the beginning, because it would be very unfair. And Demon has a winning strategy in no matter how far the game already won, to make sure that if he still has power, he has a winning strategy to keep his power up for one more round. All he needs to do here is just, well, turn the robot off and wait until he's asked to demonstrate that if he still has power, he's got power for one more control cycle. That's a piece of cake. But the two of them together, no matter how true they are, of course, do not imply that Demon would have a winning strategy in the RoboSoccer to keep his robot powered up forever, because, well, we'll need to invent an entirely new generation of batteries to make it happen. So, no, this axiom also isn't really okay for hybrid games. What about the induction proof rule over there? In that case, again, the P implies alpha box P is proved as a premise, so it's valid after the proof, so it's true in every state. You prove in every state that if P is still true, then Demon has a winning strategy in the hybrid game alpha to get to P state again. And if that's the case, then if you make sure that P was true in the beginning, Demon also has a winning strategy in the repetition of alpha game to get to P, because in every state he ever would get to, as long as he's still in the P state, which he is in the beginning, he can make one more round of alpha happen to get to a P state yet again. So that one is fine as a proof rule, but the corresponding axiomatic version of it would not have been fine. Okay, so now that we're warned about this, how about we read the regularity rule more carefully for hybrid systems and hybrid games. So what does it mean for hybrid systems? For hybrid systems, it means that if P1 and P2 imply Q, and you have a proof of that, then if all ways of running the hybrid system alpha are such that P1 is true, and all ways of running the hybrid system alpha are such that P2 is true, then all ways of running the hybrid system alpha are such that Q is true. Sure thing, because since P1 is true after all alpha runs, and P2 is true after all alpha runs, but P1 and P2 always imply Q, that also means that Q is true after all alpha runs. That's a piece of cake. Now the hybrid games reading. P1 and P2 imply Q. If Demon has a winning strategy in the hybrid game alpha to make sure that P1 is true, and he also has a winning strategy in the hybrid game alpha to make P2 true, does he have a winning strategy in the hybrid game alpha to make Q true? Well, again, not so fast. The winning strategies he needs here and there could be very different, incompatible winning strategies. For example, RoboSoccer. If you have a strong offense and you have a strong defense, then you win the game. Sure thing. There is a winning strategy in the RoboSoccer to make sure you have a strong offense. Just, keep all your robots always in the front of the game. And Demon has a winning strategy in the RoboSoccer to have a strong defense. Just pull all the robots back. But that doesn't mean he would have a winning strategy to actually win the game, no matter how amazing that would be, because the two winning strategies are sort of in conflict. You can't literally move all the robots into the front while also moving all the robots into the back of the field. You'll have to choose on the individual robots what they're supposed to do. So no, that regularity proof rule also is not okay for hybrid games. Let's look at the related one that's still okay. If, again, same premise, P1 and P2 imply Q, then if Demon has winning strategy in the hybrid game alpha to make both P1 and P2 true simultaneously, in particular in the same winning strategy because they're under the same scope of the modality, then Demon also has a winning strategy in the hybrid game alpha to make Q true, which is just another special instance of the monotonicity proof rule, so that's fine. Let's worry about the first arrival axiom, first for hybrid systems and then for hybrid games. If there is a way of repeating the hybrid system alpha to a state where P holds true, then, well, either P holds true right now in the initial state, or there is a way of repeating the hybrid program alpha sufficiently often such that P isn't true yet, but in the next round of repetition will P become true. So that's the first arrival thing. P will become true at some first point in time because either it was already true in the beginning, or we can go somewhere where it isn't true yet, but next time it will be. Now, that's the dual of the induction axiom, but is it actually okay for hybrid games? Let's see. If Angel has a winning strategy in the repetition of hers to get to a state where P holds true, does that imply that either P is true right now, or Angel has a winning strategy in the hybrid game of repetition of alpha to get to a state where P isn't true yet, but she has a winning strategy to make P true in the next case. Well, not really. For example, suppose Angel and Demon are in a robot race, and Demon has the faster robot, but Angel has the better battery. Then even if eventually Angel has a winning strategy to make sure her robot will ultimately catch the Demon robot because, well, it's got the better battery. Just wait it out, follow after Demon's robot, and even if Demon's robot chases away, ultimately it will run out of battery, and Angel's robot can slowly catch up. So she will ultimately catch Demon's robot for sure. That doesn't mean she starts in a catching state, because it would be a very boring game if she did, or that she would have a winning strategy in the game of repetition to precisely make it into a state where she hasn't caught Demon's robot yet, but precisely in the next round will she be able to catch Demon's robot. Because, all the Demon would have to do is make sure he waits until Angel is very close, so she hasn't caught him yet. But then what Demon needs to make happen is to speed away real fast, since he still got some battery left, and he's faster, so, he's going to get out of reach for Angel. And even if eventually in the long term he will have run out of battery and Angel will be able to catch him, it won't have been just then. So also this axiom, the first arrival axiom, is not actually a sound axiom for hybrid games. Now what we've got on the other side is the iteration axiom, the converse formulation of it. So let's first again read it as a hybrid system and then as a hybrid game. All ways of repeating a hybrid program alpha are such that P is true, if and only if, of course, P has to be true right now. And after all ways of repeating the hybrid program alpha, it has to be the case that all ways of running one more round of alpha are safe. So that basically means that after any number of rounds of a hybrid system are we safe, if and only if we're safe after 0 rounds and after at least 1 round. Now let's read it as a hybrid game. Demon has a winning strategy in Angel's repetition to make it to a state where P is true, if and only if P is true right now. And Demon has a winning strategy in the game of repetition to get to a state where he has a winning strategy in 1 round of alpha to get to a state where P is true. That's fine for hybrid games. Well, both sides are closely related for sure, right? Both repeat. But the difference is, in this game, Angel just stops the repetition at some arbitrary point, and Demon is surprised about it. In that game, Angel also will stop the repetition at some arbitrary point, but Demon isn't quite so surprised about it because he still has 1 more round left to play. In other words, on this side, basically, there's an advance notice of 1 round look ahead. 1 round before the end of the game, will Angel have to tell Demon, that's it, let's play 1 more round, but then it's bedtime, basically. But here in this case, this is actually, of course, easier for Demon to win. Let's make a concrete example. It's very easy to make sure that if a robot is moving now, then there is a strategy to still keep the robot moving for 1 more round, even if it has been powered off. But that doesn't mean the robot would be able to move literally all the time. It's just 1 more round is always fine because of the inertia of the robot. So that axiom, even if it shows up on this side, is not actually sound for hybrid games either. Which means we need to pay attention during our reasoning to make sure that there is no hybrid systems thought that's entering our hybrid games proving. In fact, more formally, these axioms are all unsound, and only the ones that are not crossed out are sound for hybrid games. And in fact, small side note, because both the axiomatization for differential dynamic logic that we saw, as well as the one for differential game logic that we saw, are complete, which in a technically more precise sense means something like every property for every formula that's true has a proof. That means you can now separate precisely which are the axioms that are true in one and not in the other, and you'll find out That is the ones we wrote down here. You can also actually look back and say, well, but because of the duality axiom in hybrid games, which said demon has a winning strategy in the dual game to get to P, if and only if angel has a winning strategy in the ordinary game to get to P. In other words, because of games, one game's boxes or another game's diamonds, it is, in retrospect, actually obvious why most of these aren't quite actually sound for hybrid games, because if they were, you could also swap dynamic modalities out for one another, and that certainly wouldn't be fine, for example, in the Kripke axiom, or, for example, also in the Gödel's proof rule. Just because P is a valid formula doesn't mean there is a way of running the hybrid program alpha to a state where P holds true. Because, well, maybe you can't run it at all because you'll fail some tests, and that's precisely the sort of thing that got Demon into trouble when trying to convince us that he had a winning strategy in the game. But that's not actually the explanation for all of those. For example, for the first arrival, in particular the backwards induction axiom, the unrolling a loop at the end is perfectly legitimate both for box and diamonds in hybrid systems, but it's really not okay for hybrid games. You can unroll in the front, but you cannot unroll in the back because that would be early warning of termination. Don't use axioms that do not belong to you in hybrid games for reasoning. Just be always very careful what you're doing. But now that we're primed for this, I guess soundness is a bit more subtle than we thought it would be. We really need to prove these things sound carefully, because after having augmented the syntax of the language with a duality operator and having made up for that by a vast semantic change everywhere, where we had to be prepared in the operator that there could be more adversariality and interaction happening with duality operators further down, we recovered axioms that look very tame, but we still have to justify them as sound axioms carefully because of the modified semantics. Let's do that. So the differential game logic proof calculus is sound, which means all provable formulas are valid. How do we do that? Well, we look at all the axioms and proof rules, here's some of them, and convince ourselves that this equivalence is really valid one, so true for in every state, which means for the left-hand side, we compute the set of full states in which it is true. On the right-hand side, we compute the set of full states in which it is true. And then from the semantics, we try to make an argument why the two of them are equal. Let's do so. The set of full states in which the left-hand side is true is just that, just by the semantics. That's now the winning region for the game of choice between alpha and beta to get to the set of full states in which the post condition is true. By the definition of the winning region for Angel's choice, that's the union of the winning region for the alpha subgame to make it into this post condition, union the beta subgame to make it into the set of states. That, of course, is just the exact same thing as the set of all states in which alpha diamond P is true, because that precisely means Angel has a winning strategy in the hybrid game alpha to get to a state where P holds true. And likewise, that's precisely the set of all states in which beta diamond P is true. But that union is now, of course, exactly the same as the set of all states in which this disjunction is true. Wait, that was the right-hand side. So the proof of soundness of this axiom is actually even easier than the proof of soundness was in the hybrid systems case. But we need to do it in any case. Sequential composition axiom, again, we compute the set of all states in which the left-hand side is true and the set of all states in which the right-hand side is true. And if we equate the two, then apparently the equivalence is true in all the states, so it's a valid formula. And we didn't use any specifics of what alpha, beta, and P are. So that's the winning region for the sequential composition of alpha with beta into the set of all states in which P is true. The winning region of sequential composition is the composition of the individual winning region functions, whose winning region of alpha composed with winning region of beta. The inner one is exactly the set of all states in which the formula diamond beta P is true, because that precisely means Angel has a winning strategy in the hybrid game beta to get to P. That now is precisely the set of all states in which the formula alpha diamond beta diamond P is true, which is what we wanted. Now, for the duality axiom, the argument is much more complicated, I admit, but fortunately we've already done it because that was precisely an instance of the deterministic theorem that we proved. Just to also make sure we cover one of the proof rules, the monotonicity proof rule. Now that needs a bit of a different argument. But what does it again mean for a proof rule to be sound? It means if all the premises are valid, so true in every state, then all the conclusions are valid. Now, if P implies Q is valid, so the implication is true in every state, that of course means the set of all states in which the left-hand side is true must be a subset of the set of all states in which the right-hand side is true, because otherwise P implies Q wouldn't be true everywhere. Now, in order to show that this implication, the conclusion, is valid, we show the exact same thing. The set of all states in which the left-hand side is true is a subset of the set of all states in which the right-hand side is true. How do we do that? Well, the set of all states in which the left-hand side is true is just precisely the winning region for the hybrid game alpha. To get to the set of all states in which P is true, by semantics, the winning region on the right-hand side is precisely that winning region for the hybrid game alpha also, in which the modified postcondition Q is true, and the two of them relate because since the set of all states in which P is true is a subset of the set of all states in which Q is true, that by monotonicity means the winning region that makes it into the set of all states in which P is true is a subset of the winning region for the set of all states in which Q is true because, well, Q is easier to target, it's a bit bigger than P. So, proof rule is sound as well. Notice what we've done. We observe the miracle of soundness because soundness links semantics and axiomatics in perfect unison. We have a compositional soundness argument. What we need to do here, just like in all the other cases, for soundness we need to show that if a formula P is provable, then it's valid. We also write it like this. This is what we sometimes use as notation to say that P has a proof, and if P has a proof in our calculus with axioms and proof rules, then it had better be valid, meaning true in every state. Otherwise, this would be very embarrassing for logic. Soundness is the conditio sine qua non for logic, so a condition without which logic couldn't be. You shouldn't go walk around doing proofs of counterfactual, proofs of things that aren't really true. But of course, the soundness argument needs to show that literally every formula that the proof calculus proves with any proof has to be a valid formula. Now, fortunately, proofs are composed from axioms and proof rules, so in order to demonstrate that all of those proofs are sound, we just sufficiently make sure that each of the axioms is sound, so they correspond to valid formulas, and each of the proof rules is sound, which means they take valid premises to valid conclusions, and then any proof, no matter how long it is just a combination of lots of these simpler arguments, of lots of little axioms and little proof rules. The axioms all started out with sound, so valid formulas, and the proof rules took valid formulas to valid formulas. So every step is either a sound axiom or a sound proof rule. The entire proof is going to be sound. Moreover, however, the miracle of soundness has a twist because soundness and completeness together link semantics and axiomatics in perfect unison, because you can show something like a converse. You can indeed prove that the differential game logic calculus that you saw is a sound and complete axiomatization of hybrid games relative to any differentially expressive logic. That means if formula phi in differential game logic is valid, if and only if you can prove the formula using the axioms and proof rules of differential game logic from just elementary tautologies of this differentially expressive logic. What does differentially expressive mean? It means that for every formula of differential game logic, there's a reduced formula in the sublogic that is equivalent, and equivalences to the reductions of differential questions are provable. Never mind too much about the details of that, but the highlight is that basically if you can prove sufficiently many questions about differential equations, then you can prove all true properties of hybrid games, from which, if you look at the details in the ACM Talk 2015 article, you can read off the fact that this is a constructive argument in the Moskowakis coding 3 argument, which is also minimally coding, so the only hard cases are differential equations, existential quantifiers, and box properties of repetitions, so demons winning strategies for angels repetitions, the case where angel doesn't help demon essentially. And what that means in practice is precisely that for the search for how to prove box properties of repetitions is precisely the question, well, how do you find succinct invariance? For differential equations questions is precisely the question, how do you find succinct differential invariance and things like that? And for the existential case, it's precisely the question, what's the shape of G? If it's, for example, uninterpreted, it's pretty easy semi-decidable. If it's over the reals, it's decidable after quantum elimination, Miracle by Tarski. And it turns out the only hard case is the case where you have questions such as, is there an X such that all ways of running a loop or safe, which is already pi11 complete, even for discrete programs, and of course it can't be much easier for hybrid games either. But that's not the most important thing in this course. It's just a short teaser on some theoretical properties you can read off from differential game. Another one you can read off is that differential dynamic logic and differential game logic, while being very related, are actually different. So you can also prove that differential game logic for hybrid games are strictly more expressive than differential dynamic logic for hybrid systems. So in other words, hybrid games are really more than hybrid systems. Remember, in differential dynamic logic, you can already express some form of games by, for example, saying after all ways of running alpha, there is a way of running beta, such that after all ways of running gamma, there is a way of running delta, and things like that, and then you're happy. But that was still a bounded number of interactions for this particular case. But there really is a difference. You can say more things if you're allowed to use differential game logic. Not just you can say things in better ways, but you can also strictly say more things. One part of this expressiveness is easy, the one that says, is every differential dynamic logic formula expressible in differential game logic? So the less or equal case. And that's actually really easy because every differential dynamic logic formula is a differential game logic formula, just one that doesn't mention duality. Now there's a slight twist on it, of course. Differential dynamic logic had a slightly different semantics with runs of programs, whereas differential game logic has a semantics with winning strategies and winning regions. But, well, in the dual-free case, in the case where a daemon never has any choices whatsoever at all, then the hybrid system is a single-player hybrid game, and in that case, the semantics can be shown to agree. So in other words, that's actually the easy case, because whether you call the player that's acting angel or non-determinism is irrelevant in a single-player case. The other way around is much harder, and I invite you to look at the proof for that. The corollary is that hybrid games are strictly more than hybrid systems. In fact, hybrid games are strictly more fun than hybrid systems. Let's do some proofs that we read off from the completeness. First, for example, by reminding ourselves how what we prove, not just box properties of repetitions, which we now saw as being slightly the hard part with switch of invariance, but also diamond properties of repetitions. For example, from a number of assumptions gamma, how do we prove that there is a way of running a hybrid program alpha repeatedly to a state where we reach the goal Q? Here's a concrete example of that. Well, how? I guess by finding a progress measure that takes us closer to the goal each round of alpha. So the convergence proof rule that does that asks us to find an abstract progress measure, so a formula P of the distance variable v, and prove in the beginning that there is some distance to the goal, then prove that for every distance, while we're not quite at the goal yet, if we are at the distance v from the goal, then there is a way of running alpha to a state where we're closer to the goal, so we're at distance v minus 1. And we also show that if we've become of a negative distance to the goal, or 0, then we're actually really at the goal. So whenever there is a v less or equal 0 such that p of v is true, then we're at the goal Q that we would like to be. Let's use this in this case. So in order to use it here, of course, we have to make sure in the entire proof rule that the progress distance measurement variable v isn't being tampered with by alpha, so alpha can't actually read or write the distance variable, but in principle we can just bring up a new variable as we see fit, and then use it by putting the implication proof rule over it, putting the assumption on the left-hand side, and then we dream up this variant, the formula that's making progress over time toward the goal, as opposed to an invariant that says everything always stays fine. How we do that in this case is to choose x is less than n plus 1 to be p of n, and then prove that from the initial conditions it follows that there is an n such that x is less than n plus 1. Then we fall in the middle case for n greater than 0 while we're still at that distance. There is a way of running one round to get us closer, so to the distance n minus 1. And proving that while we're at a negative distance, we're actually at the goal. Let's prove them separately. So x is greater or equal to 0, then there is an n such that x is less than n plus 1. Yeah, sure. Just choose x for n. So that's easily provable by rule arithmetic. What do we do here? Well, we apply, of course, the assignment into this, reduce it to that question, and now if x is less than n plus 1 and some other things, then x minus 1 is less than n minus 1 plus 1, which of course could have been cancelled away, which is easily provable by arithmetic as well. And if for some n less or equal 0 is x less than this n plus 1, then certainly x is less than 1 because the maximum value that n could have had is 0, which proves this too. So that's by rule arithmetic. So these convergence proofs are actually pretty easy, but on the other hand, we still need to come up with the right variant for the job. Now let's try to see another way how we can also do it. Here's, for example, for an actual hybrid game, where if we start with x greater or equal to 0, then you ask the question, does Angel have a winning strategy in the game of repetition, where each time Demon makes a choice whether he's subtracting 1 or 2 from x, and Angel wins whenever the value of x is between 0 and 2, exclusive of the right-hand side. That's a 2-nim type game. You can take 1 or 2 elements from the stack. We can prove that that's actually true. Angel does have such a winning strategy, despite Demon choosing which one. How? Well, we could try to prove it with convergence. That it turns out there's a more cute way of doing it, particularly one that's super systematic as well. This we can prove by proving it from some other stuff, which admittedly looks a bit scary, but let's understand where the additional assumptions can be made because we can prove them. What does this say? This says if we're at the goal, then there's a winning strategy for Angel in the repetition to get to that goal. Sure thing, because that's where we could start. Or if there is a winning strategy in one round to get to a state where there is a winning strategy in multiple rounds to get the goal, then there also is a winning strategy just by repetition to get to the goal. In other words, this actually is an instance of the iteration axiom, and because that's provable, it will also be provable with the universal quantifier in front of it, because everything that has a proof also has a proof with additional universal quantifiers in the very top, just by the all right proof rule or Skolemization. So we can safely make this assumption here because there would have been a proof for it. Admittedly, this looks much more scary now to prove because there's more stuff in it. But what we've done here is basically characterize the fixed point condition for the repetition, right? Where if we're at the goal, then repetition would have been, or if one more round would have gotten to where the repetition would have gone to, then we're in the case where repetition works. Still, looks fairly complicated. Now what we can do by the uniform substitution proof rule, the one that is able to take predicate symbols and replace them with concrete formulas under a careful substitution mechanism, is to say we can call alpha star winning just p of x as some condition in the state x. And all of a sudden it looks much simpler. It still has a lot more logic around, I admit that, but on the other hand, at least the repetition went away, so we made it structurally simpler. That's what we need to prove it. Now what we can do is work on alpha, which now has just no more loops, and say, well, Here we're asking whether Angel has a winning strategy in Demon's choice, which of course requires her to have a winning strategy in both of the possible outcomes the Demon could be choosing. So both when Beta runs and when Gamma runs. Okay. Now, by the assignment, x minus 1 is plugged in for x, so we're asking the question whether p is true of x minus 1. And here, x minus 2 is plugged in for x, we're asking the question whether p is true of x minus 2. And now what we've got here is actually just arithmetic, although admittedly arithmetic with uninterpreted predicate symbols, but let's convince ourselves that it's true. So, if we're between 0 and 2, then p is true of x. So let's plot that. So 0 and 2, then in this interval do we know is p true? The next thing says that p is true of x if it's true of the predecessor and the predecessor's predecessor, which certainly if you go up to the value 3 should be true for all points here, because for example this one, its predecessor and its predecessor's predecessor is actually true. Because remember the 1 is right here. But now up until 4 we can still make the same argument, because its predecessor and its predecessor are already in the set. So in other words, all the numbers greater or equal to 0 will be numbers that p is true of, and that's precisely the question we ask here. If x is greater or equal to 0, then is p of x true? And yep, it is by this arithmetic gadget argument. Likewise, in the proper hybrid game, here we ask the question without any precondition, whether Angel has winning strategy in the game of her repetition, where every time she gets to decide whether she wants to play left or right. If she plays left, then the value of x is reset to 1, and control is given over to Demon, who can follow a differential equation x prime equals 1 for any amount of time, and in the right subgame x is just subtracted to have x minus 1. And the overall question for Angel is, does she have a winning strategy to get to a state between 0 and 1? Let's prove that with the same technique. Then what we've got here is we again would cut in a proof of the iteration axioms instance with a universal closure in front of it. Then observe that all the occurrences of the loop we can call p of x. Now the loop is gone, that's good, after this fixed point characterization used in the middle of the proof. And now we can work off beta choice gamma, which we've got here, and say, since Angel gets to make the choice now, it's a disjunction of the two. On beta, it's a sequential composition, and then a duality operator. So the duality operator turns into double negation. And here it's a direct assignment, so we ask whether p is true of x minus 1. Now we solve the differential equation here, which is of course easy to solve in this case, which is just there is a duration that we insert into x plus t, which is the solution of this differential equation, such that the postcondition not p of x is true. Now we plug the assignment in, so this assignment goes here, well that assignment goes there. So overall what we've got is the question with the not exists not flipped into a for all. The question whether p of x is true between 0 and 1, or if it's true of the predecessor, so is true until 2 and is then true until 3 and 4 and dot 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 dot, or if it's true for all numbers greater or equal to 1, which of course at some point will be here, so it's true for all of them, and that means it's now true for all of the numbers, which is precisely the question here. Is p of x true when the assumption is true, which was actually just nothing, just true, so the whole thing can actually be proved at real arithmetic with uninterpreted predicate symbols as well. Now that we have achieved a very thorough understanding of hybrid games proving and how it exactly contrasts with hybrid systems proving, we can already make our life more interesting, more challenging admittedly as well, by taking a short detour with an expedition into differential hybrid games. Why? Well, because everything we saw so far was proving for hybrid games, but we just on the differential equation side literally looked at the solutions axiom, which of course we already understand in the second part of the textbook to be pretty impoverished. Now, everything we said in the second part of the textbook about differential invariants and differential cuts and differential ghosts, of course, also still works in the differential equations that show up in the middle of hybrid games, but I would like to take this opportunity to look into other ways how we can take multidynamical systems principles to heart and look at how discrete continues and adversarial dynamics interact and mix. How so? Well, because discrete dynamics, continuous dynamics, and adversarial dynamics already interact quite closely in hybrid games, but there's another way to make them interact by having straight out the continuous dynamics and its adversarial dynamics interact right during the continuous dynamics in the middle of the differential equation, where at the moment interaction was limited to just one of the players, namely Angel, choosing how long to evolve, and the other player, Demon, sat by and just was watching the show. All of the interaction of Demon into the play was in the hybrid games part of it, and not really during the continuous dynamics. But there is a way of doing that as well, by taking multidynamical systems principles directly serious. So let's understand how that happens in differential hybrid games, so the games that mix discrete and continuous and adversarial dynamics pretty freely. By extending this language yet again, hybrid games become differential hybrid games by us adding differential games into the programming language, where this differential game no longer is just a differential equation, x prime equals f of x, but all of a sudden the differential equation, its right-hand side, is also depending on an extra vector of variables y and z that the two players choose. So what this notation means here is that Demon controls the control input variable y within some compact set capital Y. Having done so, Angel controls the right-hand side of the differential equation by choosing the vector of variable z within some compact set capital Z. And the order of notation, so the duality indicates that this is Demon's choice, while this indicates that that's Angel's choice. But the order of notation also indicates that it's Demon who chooses before Angel does. And also, just like in the differential equations case, it is Angel who decides on the duration. In particular, this is now a differential game where the time derivative of a position is not just a function of the position, but also a function of, well, the present inputs of the two players, who of course can change their mind over time. So overall, the behavior of this differential game is actually a function that depends on the function over time, how y changes and how z changes. And in fact, it turns out to be mathematically quite sophisticated to make the semantics sufficiently rigorous for any proofs and well-defined about it in these differential games. So that's not what I would like to go into. Instead, I would like to go into an application of that to give you some intuition for it in the Zeppelin obstacle parcours scenario, where you're controlling this airship or Zeppelin, and there's a number of obstacles. Plus, there's wind fields that the Zeppelin is subjected to, and the Zeppelin airship needs to avoid the obstacles despite changing wind conditions. The wind is blowing in this direction, and blowing in that direction down there, and blowing in this direction. And on top of the systematic wind field going always in the same direction in each of those parts of the world, there's also local turbulence that's wiggling the Zeppelin aircraft around. And in particular, all of a sudden you have this multiple scale phenomena that the systematic direction of the wind changes every once in a while, and of course there's no reason to hope that the wind would always be helping us, so we have to admit him as an adversarial player into the system. The environment player is changing the wind, but also locally always there's a little bit of extra turbulence that's making the wind look a little bit different than the systematic trend, which of course also isn't under our control when we're controlling the Zeppelin aircraft. But it would be changing at a much quicker pace, the local turbulence, than the systematic change of the wind field, for example, here and there. And in fact, what you now do is follow the differential game where, the turbulence is acting on the airship while our propeller of the airship is making the propeller turn into different directions and varying in magnitude as well. And so the result of this play or interplay by the local turbulence with the propeller and the systematic wind field make the Zeppelin fly, and then maybe the wind field changes and fly over there, and changes, and da, 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 da. The question is, how, from what control states, and under what circumstances can you control the Zeppelin airship correctly? Let's develop such a model where we've got, let's say, just one obstacle at a time to worry about of a certain radius c. So this one is a bigger one than that's a smaller one. Now, in a loop, we ask whether Demon has a winning strategy to stay far enough away from the obstacle, which of course is only possible if we started far enough away from the obstacle, where every once in a while in this loop, a discrete game change will assign a new wind field velocity, a new obstacle position, this one, that one, that one, and the new radius of the obstacle, this one, that one, that one. Under certain conditions C, of course, we can't accept any arbitrary changes of wind fields and obstacles because right in front of our noses would be really bad. There is a logically precise condition C that you can look up in the ACM Tocqueville 17 paper. But the point is, this is discrete game interaction because it's the opponent of the demon player, namely Angel, doing that. But you then also follow a differential equation, in fact, a differential game, where the position in 2 dimensions of the airship is changing with the velocity of the wind field in 2 dimensions, so being blown this way, being blown that way, being blown this way, plus the propeller of the airship. So y is a direction in the unit ball, so something that squares to at most 1, with which you can control the direction and also the magnitude, but everything only within unit ball. And the factor P is a constant, says how strong is your propeller that you can use for control. And the local turbulence is acting on it. Also Z is chosen from among a unit ball, but it's the opponent, Angel, choosing that. So angels are controlling the wind and the local turbulence here, and Demon is in charge of flying the airship. And also with some strength of the local turbulence R pushing and pulling in some direction Z. This is now the much quicker interaction differential game that we're following, which is giving us these paths, for example, here. So what you've got overall is an airship at a 2-dimensional position with a propeller that's controlled in any direction, sporadically by the opponent changing homogeneous wind fields in 2 dimensions, sporadically changing obstacles in 2 dimensions with a certain size, subject to some constraints, but continuously local turbulence of magnitude R acting in the direction Z. Now, if we ask ourselves whether there is such a winning strategy for the pilot Demon, then there's a couple of different cases to consider. The one is, what if the turbulence's magnitude is bigger than the airship's propeller strength? Well, in that case, it's completely hopeless because the turbulence always is stronger than the propellers, or anything that the propeller is trying to do, the turbulence could overrule and the airship is hopelessly tossed against the obstacles, for example. What if the propeller is stronger than the norm of the wind field plus the turbulence together? Well, then it's the opposite, right? In that case, the propeller is so overpowered that it, just no matter what the wind field and the turbulence could possibly ever do to it, it always wins over. So that's the easy case. It's provable that there is a way of providing obstacle avoidance under those circumstances, but it's also kind of sort of a little bit the boring case. what if it's in between? What if the power of the propeller is more than the turbulence? So it's not hopeless, but also not as much as to actually overpower the wind field and the local turbulence. Well, that's our challenge. That's a really interesting, hard question where the airship needs to be very, very clever in terms of navigating this big parkour, because if he's not paying attention, he might get trapped into corners that he can't avoid collisions with obstacles out of anymore. How to do that? Well, in that case, of course, there's hybrid games proving that we already understand very well, but there's also differential games proving, so the ones where we follow a differential equation, but there's input by the two players. And in that case, what you can do is not solve the differential game, right? Because that's kind of sort of pointless. We already saw with differential equations how pointless it is to try to solve them, because most of them don't have solutions. But at the latest with differential games, it's really hopeless, because now the solution over time of x depends on the input y and z that the two players choose, which is an entire signal of how y and z values change over time. And that's really complicated, because all of a sudden the solution will be parameterized by a family of two inputs of functions over time which respond to each other and so on. That's very, very complicated. No, instead, the better way is to listen to how we've done proofs for differential equations in part 2 of the textbook by proving them inductively without worrying about their solutions, just from proving the right-hand side. And the exact same principle works here as well. So it is the differential of f that's telling us in what direction does the system evolve. But since even if we're interested in what direction does our truth value of a post-condition get better, the problem is that there's not just us pulling in the direction, but there's also the opponent angel pulling in the direction. So we need to take that into account. And how that works is that we say, well, there's the differential of f, all right, and I guess it still stands to reason to assume that x prime is the right-hand side of a differential equation, just like it was in differential invariance. What do we do with the control inputs? Now, the problem is that these are functions over time, and we cannot just quantify and parameterize this thing with functions over time and try and solve it. That won't work. But what we can do is benefit from the locals perspective we had in the differential invariance case as well. We are proving this by proving it locally. And so what locally do we need to do with these two? Well, locally there's a choice of y, and locally there's a choice of z. And I guess y had better be in y, and z had better be in z, otherwise they would have used control inputs that are outside the legitimately usable parts of it. So that won't be work. Now, who gets to choose and why and how? Well, I guess Demon gets to choose y. So since we're trying to prove it existence of Demon's winning strategy, this is an exists of y. And Angel gets to choose z. Demon can't help how Angel does it, so that will have to be a for all z. Now, in which order do the two of these go? It's of course super subtle, but the point is that the semantics of this goes in the order of notation. So first, Demon chooses y, and then Angel chooses z. So she has a bit of an information advantage. Indeed, because of that reason, if we prove that there is a y such that for all z's and z, this condition works out, then we have a correct proof rule, the differential game invariant proof rule, which of course also still works in exactly the same way in the cases where y and z don't even occur, in which case, of course, it's irrelevant what it's chosen from, in which case it's irrelevant that we quantify over these, and we've got the familiar differential invariant proving principle back again. But the more interesting case is, what if there is actual input by the two players? Likewise, there's differential game refinement principle, where we say if we have one differential game where we would like to make f happen for Demon, and another differential game where we'd also like to make f happen for Demon, then how do the two relate? Well, in that case, if for every control that Demon would like to do in the assumption, if there is a corresponding control and the other game that he still has, but also for every control that his opponent Angel could choose against him in this one. There already is a control in the assumptions game here, such that in every position that the game could be in, f of x, y, z equals g of x, u, v, then you have a differential game refinement argument, an argument how if this game can be won, that game can be won as well. But one step at a time. First, let's look at differential game invariance in action. For example, if x cubed is greater or equal to 1, then along the strength game, a demon has a winning strategy to make sure x cubed is greater or equal to 1, where the differential game follows x prime equals -1 plus 2y plus c, where both y and z are chosen from the interval between -1 and 1. But demon's y is a little bit stronger. Now we prove this just by using the differential game invariant principle. So we prime the post condition. So that gives us 0 is less or equal 3x squared x prime. And we keep a discrete shadow of the differential game around. So x prime is assigned to be the right hand side, -1 plus 2y plus c. And we asked, is there locally a choice for demon, such that locally every choice for angel makes this thing happy? And yes, there is, because if we plug this in, the right hand side, then we've got the question, x squared is always greater or equal to 0, but what about this? Well, and there is a choice for y, such that this is greater or equal to 0, no matter what z is doing, because 2 is bigger than the -1, and at most the 1 that z could be. So yes, this has a proof very easily. Of course, this was kind of an easy question because, well, I guess this is a strength game where 2 is stronger than that one. Now, what about the lion and man game in 2 dimensions, where if the lion and man are still far enough apart, is there a winning strategy for demon to make sure they're still far enough apart, where now in different differential equations, which are part of the exact same differential game, we follow the 2-dimensional position of m is following in direction y, which is demon's input with velocity m at most, while the lion is following in direction z, angel's choice, so angel's controlling the lion, demon is controlling the man with velocity l at most. Then if the man isn't slower than the lion, then there is a way of winning this as well. But we prove it not by solving, but by forming differentials over it. So this is just 2l minus m times scalar product, the inner one derived, so l prime minus m prime, and of course m prime is my, and l prime is lz. So we plug that in. And then indeed, there is a vector in the unit ball, such that for every vector z in the unit ball, this scalar product is at least 0, so it's greater or equal to 0, because if L is a little bit weaker than M, you can make this happen by appropriate choices. Likewise, that was now focusing in on the box case, a demon's winning strategy, where Angel's in charge of time. But what about Angel's winning strategy since she's in charge of time? Well, in that case, you can do something that's also possible for differential equations, but I only talk about it here for differential games right away, where, well, if the opposed condition, in this case g greater or equal to 0, is already true in the beginning, then it's really boring to prove that you have a winning strategy, because, you know, following this for 0 time units would do it. So it's only really super exciting if we don't assume that g is greater or equal to 0 at the beginning yet, but then we prove that g is becoming bigger and bigger, or rather that there is a winning strategy in this differential game to make it so. How does that work? Well, in that case, you not only need to show that there is a way for g to make progress, but you also need to show there is a way for g to make sufficient progress. So at least, you know, not just progress by a foot and then half a foot and then a quarter of a foot and all kinds of things, smaller, 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 which never gets you anywhere, but there is progress by at least an inch. Okay, so what we need to make sure is that the system is along a differential game making progress toward a goal region F, well, in this case g greater or equal to 0, to show that even if this is wiggling around, so even if the opponent is acting on it, we can also still act on it in Angel's behalf to make sure it is getting to the goal. How that can be proved is by showing that there is a minimal progress epsilon, which is positive, such that everywhere, no matter where we are, there is a way of controlling Angel's input Z, such that no matter what the opponent Y is doing, if we're not at the goal just quite yet, so if G is still less or equal 0, then we're inductive. That means ultimately the lead derivative, but that means the differential of G with the right-hand side of a differential game put in for the variable or x prime representing the left-hand side is at least epsilon. We'll notice that the order of quantifiers is slightly conservative here, so even if demon Y chooses first, Angel Z chooses second, here we've swapped the order, which is conservative and sound. With that, for example, you can prove that in a spiral game, you can make sure that 1 minus x squared minus u squared is always greater than 0, where x prime is following zx minus yu, and u prime is following zu plus yx, where demon is choosing between minus 2 and 2 the y, and Angel is choosing between minus 1 and 1 the z. So Angel is actually the weaker one, but it still works out because by using the differential game. Variant proof rule, you ask, is there an epsilon such that everywhere we are in x and u coordinates, there is an Angel's choice such that no matter what demon could do, if we're not at the goal yet, we'll get to the goal. Where here I delighted the right-hand side just because of space reasons. And the differential of this is just minus 2x x prime minus 2u u prime, greater or equal epsilon, remember? And that indeed, you plug it in and you're able to prove, which tells you that yes, indeed, even if Angel is the weaker one of the two, she has a winning strategy to make sure that this is ultimately greater or equal 0. Coming back, the Zeppelin obstacle parkour, you can use precisely the reasoning techniques I've just shown you to prove that there are winning regions where the opponent, the wind, has a winning strategy to make the Zeppelin crash. But there's also regions where there is a winning strategy for the Zeppelin aircraft to remain afloat without collision. And it turns out in this particular differential game run that we've tried here, we were very lucky because even if it didn't collide, that's in the middle of a region where the wind and turbulence together would have had a winning strategy to make the obstacle collision happen. And so it was just a way of luck that it didn't collide, which was a stupid strategy, which in particular, of course, means since we were still in the winning region before that, let's say here, the Zeppelin pilot should have chosen a action that keeps it out of this provably unsafe region and within the provably safe region. In fact, it also turns out that up here where we started, the aircraft was in a provably unsafe region, so if only the wind and turbulence had really tried, they would have gotten the Zeppelin aircraft navigated down there. But the same wouldn't have happened if only the airship had started here. These things you can prove. Let's summarize what we've seen in this chapter. Differential game logic, which is the logic of hybrid games, and is a compositional programming language and logic, which in very free ways mixes discrete, continuous, and adversarial dynamics together in a truly multidynamical systems way. Granted, the semantics and activities were rather challenging. For example, remember how the winning region's iterations were bigger than omega power omega in some hybrid games, so bigger than sort of infinity power infinity, which sounds pretty scary, but we nevertheless found a sound and relatively complete axiomatization for differential game logic, so it's surprisingly tame, even though we've seen that hybrid games are strictly more expressive and also strictly more fun than hybrid systems. So while on the one hand, the duality operator was turning out to be a very radical challenge in many ways, we observed logical robustness at its best, so it was still a pretty surprisingly smooth extension where many of our reasoning principles just stayed afloat and still worked, and even completeness could be covered for that. But the main lesson for you from today's chapter is that you really shouldn't be using systems thinking for games, because even if they share many similarities, as we've seen from some unsound axioms that are only okay for hybrid systems but not for hybrid games, there are also differences that we need to pay attention to, at least whenever we do reasoning and proofs on a sheet of paper.